Hi, everyone. So today we are going to be reviewing our radicals, section 8.1 and 8.2, which begins our unit slash chapter 8. So the learning objectives for today are being able to simplify expressions with roots, simplify variable expressions with roots, and then use the product property and quotient property to simplify our radical expressions. Why don't we start with a few warm-up problems? Our first question asks us to simplify the following. So we have -9 in parentheses squared is the same as just a -9 times -9, which gives you +81. Part B, we don't have the parentheses anymore, so we first solve 9 squared, which gives us 81, and then we tack in that negative in the front. So -81 is our result for part B. And then part C, we are looking at a cube now, where we have -9 times -9 times -9, which gives you a +81 times -9. And then a positive times a negative is and 81 times 9 is 729. So our final result is negative 729. And we're done. Let's move on to question 2. Properties of exponents, x to the third times x to the third. 3 plus 3 is 6, so we get x to the sixth. Part B, y to the second times y to the second times y to the second. 2 plus 2 plus 2 gives you 6, so we get y to the sixth. And then third, z to the third times z to the third times z to the third times z to the third. 3 plus 3 plus 3 plus 3, same as 6 plus 6, which is 12. So z to the 12th power. Okay. Our first objective, being able to simplify expressions with roots. And so the square and the square root of a number are inverses of one another. When you square something to take the opposite, you are going to take the square root. And then this is just some proper terminology, I would say, or just proper English vocabulary where 3 squared is read as not 3. 13 squared is read as 13 squared. And then 169 is called the square of 39. Or you can say 13 is a square root of 169. So just some lingo to reinforce into your brain. And then we have our square root notation, which is this squiggly looking fella. So if we were to take the square root of 144, what number times that same number will give you 144, and that's 12 times 12. So the square root of 144 is equal to 12. Okay, let's look at our example 1. We're asked to find the square root of 144. And then the square root of -289. There are many, many times where we neglect the negatives when we're taking square root, but it's important to be mindful of that. So square root of 144 could either be 12 or -12, and we can rewrite this as plus or minus 12. But if you're dealing with solely distance, then you end up rejecting that negative. We were looking at negative square root of 289. Once again, just the square root of 289 would give us either a positive 17 or a negative 17, aka plus or minus 17. And then we have this negative in front. And so that really doesn't change the results. A negative times a positive is a negative, and a negative times a negative is a positive. So you're once again looking at negative or positive 17. Does it matter if the plus is on the bottom or the plus is on the top? No, these are just your two potential solutions. You could even just keep it as plus or minus 17 here. And then once again, if we are solely talking about distance underneath that square root sign, then we actually would have to reject this negative value. And then your final result after you multiply it by a negative would actually be just negative 17. So just be mindful of that. It's good to know both. Okay. What if the negative is inside of the square root symbol? We're looking at the square root of negative 49. Do we have any two real numbers multiplied together to give you a negative 49? These two numbers being of the exact same value. We actually don't in the real number system because a negative times a negative gives you a positive, and a positive times a positive gives you a positive. So the only way to yield a negative is to multiply a positive by a negative in the real number system. And so do we not have a solution whatsoever? That's not true. We do have a solution. It's just our solution has now entered into the imaginary world. So our solution here is no longer real. It's imaginary. Okay. Now let's try these two examples together, and we're just gonna, for straightforward purposes, reject the potential negative solutions. What do I mean by that? The square root of 100 plus or minus 10, we're just going to say, okay, square root of 100 is 10. So when we look at A, we have, okay, what's the square root of negative 196? This can actually be broken into the square root of positive 196 and the square root of negative 1. And this negative 1 is a famous fact for our imaginary numbers. This represents I. In other words, I times I gives us I squared. And I squared is equal to negative 1. Okay. So first fun fact for today. And so now we can replace that square root of negative 1 with I. And the square root of a positive 196 is just 14. So our final result is 14i. We do want to mention, once again, there's no real solution here. Just imaginary. And what is our imaginary solution? It's 14i. Okay. All right. So let's move on to our part B. Just gonna fix that. Our part B is now asking what's the square root of negative on the outside and then 64. Again, we're going to reject that negative symbol. So we're just looking at positive 8 for square root of 64, and then we have that negative tacked on in the front. So final solution is negative 8. And we're done. Some vocab to keep in mind. N squared, n cubed, n to the 4th power, n to the 5th power, n to the 28th power, so on and so forth. And then these are some famous values to remember from the squared, cubed, 4th power, 5th power perspective. We have 2 to the 2nd is 4, 2 to the 3rd is 8, 5 to the 2nd, 25, 5 to the 5th, 3,125, so on and so forth. Another thing to keep in mind, if you have even degrees and you're dealing with negatives, all of the even degrees shoot to positive, all of the odds remain negative. And then from the root perspective, we deal with the vocabulary word known as our index. And the index is just a small little tiny number that tells us what root we're talking about. So this n here represents the index. For example, let's say we were taking the 15th root of 1500, or the cube root of 81. 3 is our index for that second one, and 15 is our index for the first. These are just our properties of our roots. If we're dealing with a real number, we want to make sure that our a value underneath that root symbol is either 0 or positive. And then if we end up entering into the imaginary world, then our a can actually be less than 0, which means it's no longer a real number. And then this is just when n, our index, is an odd number, then it does not matter if there's a negative underneath the root, we'll always be in that real number system. Okay, let's jump into example 3 together. We have cube root of 64. What times what gives you 64? Simply not 8. 4, right? 4 times 4 is 16. And then 16 times 4 gives you 64. All right, well, what about part B, the 4th root of 81? What times what times what times what gives you 81? It's 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. And then part C, we're asking, okay, what times what times what times what times what gives you 32, aka the 5th root of 32, and that's just 2. 2 to the 5th is 32. Let's look at example 4. Notice we have some negatives underneath the roots. Part A, we're taking the cube root of negative 125. Since it's cube, we have an odd index. Works in our favor because we'll remain in that real number system. What times what times what gives you negative 125? It's just negative 5. Part B, the negative is on the outside, so that doesn't conflict. And then we have the 4th root of positive 16. Well, we know that 2 to the 3rd is 8, which means 2 to the 4th is 16. So the 4th root of 16 is 2. tack the negative in the front, and we get -2. Done. And then last but not least, we have the fifth root, odd index again, of -243. It's negative, but it doesn't matter because our index is odd. And so what times what times what times what times what gives you that -243? Well, we have a -3 times a -3 is -9, or +9, sorry. +9 times -3 is a -27, times a -3 is a +81. And then 81 times -3 is a -243, which means our answer is -3. And we're good. Our objective 2, we're asked to simplify variable expressions with roots. And so this is just dealing with, think about simplifying radicals where, for example, square root of 8, we can pull out the square root of 4, which is a perfect square, and then 4 times 2 gives you 8, simplifies to 2 square root of 2. So we're doing the same thing, but our index might not be 2, it might be 3, it might be 4, it might be 5. So our index is changing, but we want to still be able to simplify to its fullest. And this is just a notes page with simplifying odd and even roots. Box it for you. And so when our index is odd, what are we going to end up getting? Our nth root of a to the n is n, but when our index is even, we can get both negative or positive a, right? The absolute value of a, whether a is negative or positive, will be our solution. Just like square root of 100, right? Index is 2, we could have either plus or minus 10, whereas the cube root of positive 81 is going to be, or sorry, let's do the cube root of positive 27. We only have one solution. We only have 3. 3 times 3 is 9. 9 times 3 is 27. It's not -3 because -3 times -3 is +9, and +9 times -3 is -27. Okay. Example 5. We're looking at the square root of x squared. Final result, this is when we want to include both the plus and minus based off of the indexes being odd or even. So we have plus or minus x. Part B, odd index, one solution. Cube root of n to the third, we just have as n. Part C, even index, the fourth root of p to the fourth, we have plus or minus p. And then last but not least, the fifth root of y to the fifth, odd index, one solution, and we just have y. And we're done. Another notes page. What about square roots of higher powers of variables? So we have our power property of exponents, meaning if we have a term that has an exponent and then we raise it to another exponent, what are we doing to those exponents? We are taking the product of them. A to the m raised to the n is a to the m times n. And so if we square am, the exponent will become 2m. And I'll show, well, actually, they kind of show it to you right down here. I was going to write it out, but am raised to the second power is the same as a to the m times 2, which is same as a to the 2 times m. And so now looking at this from different variations, we just went over this part. But if we were dealing with our index to be even, we still get those two solutions. So we have square root of a to the 2m. This is the same as the square root of a to the m raised to the second. And that's the same as plus or minus a to the m, which is just the absolute value of a to the m. So what does this tell us? This tells us that the square root of a to the 2m is plus or minus a to the m, also known as absolute value of a to the m. Knowing this, let's jump into example 6. Square root of x to the 6th, our index is even, so we're going to be dealing with plus or minus as our final solution. And this is the same. We can put this all in terms of fractional exponents. And so x to the 6 over 2 gives us 3. So our final result is plus or minus x to the 3rd, and we're done. Now let's look at part B, which has an odd index, so one solution. Fractional exponent, raise it to the 1/3. 3 goes into 18. 6 times our final solution, y to the 6th. And then finally, let's look at part C, even index, 2 possible solutions. Notice how we have a coefficient here now. So we can break this up separately if it makes it easier in your head. The 4th root of 16 and the 4th root of q to the 12th. What times what times what times what gives you 16? That's 2. And then again, 2 solutions, so it's a plus or minus. And then we have q to the 12 divided by 4, which is just q to the 3rd. So our 2 solutions are plus or minus 2q to the 3rd, and we're done. It will get a little bit more complex. What if we're dealing with 2 variables? Procedure is the same, we just have more terms or more variables to deal with. First one, square root, even index. We can think about these separately. What's the square root of 36? What's the square root of x squared? And what's the square root of y squared? Well, it's an even index, so we have plus or minus. The square root of 36 is 6. Square root of x squared is x. Square root of y squared is y. Final answer, and we're done. Let's do the same for the second, which is once again even index. So we have a plus or minus. Square root of 121 is 11. Square root of a to the 6th. 6 divided by 2 is 3, so we have a to the 3rd. And square root of b to the 8th is the same as 8 divided by 2, which is 4, so we have b to the 4th. Final answer. And then last but not least, we have a cube root, so we have one solution. Let's once again take this separately. We have the cube root of 64. What times what times what gives you 64? 4 times 4 is 16. 16 times 4 gives you 64. So we have 4. And then we have the cube root of p to the 63. How many times does 3 go into 63? It goes in 21 times, so p to the 21st. And then we have the cube root of q to the 9th. How many times does 3 go into 9? It goes in 3 times, so q to the third. Once again, one solution. It's an odd index, and we're done. All right, so that was the end of our section 8.1, and now we're jumping into our 8.2, which we're stepping up, going into a few more complex examples. But let's start with some warm-up problems, really reviewing our properties of exponents. So part A, when you divide numbers that contain the same base, you subtract the exponent. So we have x to the 9 minus 4, which gives us x to the 5th to be your final result. In part B, y to the 3 minus 11 gives you y to the negative 8, but let's not have negative exponents. This is the same as 1 over the positive version, which is just y to the 8th. And then finally, our second problem, when you raise a term to an exponent, you multiply those exponents. So 2 times 6 gives you 12. Final results, n to the 12th. We have our third objective for today's lesson is to be able to use that product property to simplify rational expressions. And then we have some paragraphs to read. I'll read both of them since I don't have any students in front of me at the moment. So we will simplify radical expressions in a way similar to how we simplified fractions. A fraction is simplified if there are no common factors in the numerator and the denominator. To simplify a fraction, we look for any common factors in both the numerator and the denominator. And then we have a radical expression. Our general form is that nth root of a. It's considered simplified if it has no factors of m to the n. So how do we simplify rational expressions? We look for any factors in that radicand that are powers of the index, and then we go from there. These are just the formalized definitions for simplifying radical expressions, as well as our product properties of nth roots. And then we have a slide on the step-by-step procedures in how to simplify a radical expression using our product property, but we'll go through it step by step in our concrete example coming up. So we have 3 parts to this example 8. Let's get into it. Our part A, we want to find the square root of 500, so we'll keep it nice and straightforward for now. Just dealing with numerical values for each of these. And going from square root to cubic root to the 4th root. So for the square root, we ask, okay, what is the highest perfect square that goes into 500? And that's 100. How many times does 100 go into 500? It goes in 5 times. And we know that the square root of 100 is 10. Square root of 5 cannot be simplified further. So our final simplified radical form is 10 square root of 5. Now we're looking at the cube root of 16. So we want to ask ourselves, always start with the lowest one, not 1, because 1 doesn't really do anything for us, but let's jump to 2. Our index is 3. So 2 to the 3rd power, 2 times 2 times 2, oh, that's 8. Is 8 a factor of 16? Ooh, it is. So what can we do here? We can break this up into the cube root of 8, and then 8 times what gives you 16? 2. So we have the cube root of 8 times the cube root of 2. And we know the cube root of 8 is simply 2. And the cube root of 2 can not be simplified further, so our final result is just 2 cube root of 2, and we're done. And then finally, we're on that last part, part C, and we're looking at the fourth root. So again, start off low. We'll start off with 2. 2 to the fourth power. Well, we know 2 to the third is 8. 2 to the fourth is 16. Does 16 go into 243? And it does not. So now let's jump up a little higher. What about 3 to the fourth? 3 to the second is 9. 3 to the third is 27. 3 to the fourth is 81. And does 81 go into 243? And it should. 81 goes into 243 actually 3 times. And so we kind of just got our answer here. But I'll show you it broken up. We can break this up into the fourth root of 81 and the fourth root of 3. And actually, I don't think we can even break it up like that because we can't solve it then. We'd have to keep it together. Essentially, what we're asking is, okay, what number times what number times what number times what number gives us 243? And if you know that 3 to the third power gives us 27. Oh, actually, we should have broken it up. For some reason, I was thinking in my head 3 to the fourth is 243, but it's not. It's 3 to the fifth is. 3 to the fourth is 81. 3 to the fifth gives you that 243. So let's go back to what I wrote a moment ago, breaking this up into the fourth root of 81 times the fourth root of 3. And we know that the fourth root of 81, solved it over here, it's just 3. But the fourth root of 3 cannot be simplified further, so our final result is just 3 times the fourth root of 3. And we're done. Let's look at example 9 together. Another 3 parts. We have, once again, a square root. 72 n to the 7th. So think about perfect squares. 9 goes into 72, but is there a greater one? Ooh, 36, right? So we can break up the coefficient into 36 and 2. And then n to the 7th can be broken up into n to the 6th and n. And so we can simplify that square root of 36 and that square root of n squared quite efficiently. And the square root of 2 cannot be simplified more, and neither can that square root of n. So we end up with square root of 36 is 6. Square root of n to the 6th is n to the 3rd. And then we have times the square root of 2n, since that cannot be simplified further. And we're done. Let's jump into now our cubic. So we have the cube root of 24, x to the 7th. And once again, start low. So 2 to the 3rd is 8. Does 8 go into 24? It does. How many times? 8 goes into 24 3 times. So we can break up the coefficient into the cube root of 8 times the cube root of 3. Now, cube root of 3 cannot be simplified further, right? What times what gives you 3? It's a number between 1 and 2, closer to 1. But let's look at our variable. We have x to the 7th power. Let's break this up. We can break this up into the cube root of x to the 6th times the cube root of x. And so once again, which ones can be simplified? Cube root of 8 and the cube root of 6. Which ones can't? Cube root of 3 and cube root of x. So what can this be simplified to? Cube root of 8 is 2. Cube root of 6, how many times does 3 go into 6? It goes in twice, so x squared. And then we're left with the cube root of 3x in our light pink. And we're done. Last but not least, let's look at now our quartic root, aka the 4th root of 80 y to the 14th. Start off low. 2 to the 4th power is 16. And does 16 go into 80? It does. It goes in 5 times. So we can rewrite the coefficient as the 4th root of 16 times the 4th root of 5. And then y to the 14th, how many times does 4 go into 14? It goes in 12 times. Not 12 times. It goes in 3 times because 4 times 3 is 12. So we have the 4th root of y to the 12th. And then we have the 4th root of, what's the remaining? That 2, right? Y to the 2nd. And so which ones can be simplified here? Our yellows. Which ones cannot? Our light pinks. So this ends up being 4th root of 16 is 2. 4th root of y to the 12th is y to the 3rd, because 4 goes into 12 3 times. And then in our light pink, we're left with 5y squared, and we're done. Let's do some more examples together. A lot of examples during this section. Okay. So we have another square root question. It's always good to become a master in taking the square root of radicals or radical expressions. And then we have a cube root. Okay. So for part A, let's look at the coefficient first. What's the largest perfect square that goes into 63? We have 9. 9 goes into 63 7 times. And then u to the 3rd can be broken up into u to the 2nd and u. And v to the 5th can be broken up into v to the 4th and v. So highlight the ones we can simplify in yellow, and the ones we can't in our light pink. And our final solution, square root of 9 is 3, square root of u squared is u, square root of v to the 4th is v to the 2nd. And then everything else in pink, we're left with 7uv, and we're done. Also, you just want to keep in mind all of the even indexes. We have 2 solutions, so plus or minus. And we should really put that in for those previous examples. All even indexes. All odd ones have 1 solution. All right, great. Part B, now we're looking at cube root. Again, start off small. 2 to the 3rd is 8. Does 8 go into 40? It does. 8 goes into 40 5 times. So we can break this up into the cube root of 8 times the cube root of 5. And then we have the cube root of x to the 4th. Well, that's the same as the cube root of x to the 3rd times just the cube root of x. And then we have the cube root of y to the 5th. That's just the same as the cube root of y cubed times the cube root of y squared. Now let's highlight the ones we can't simplify any further. And then let in our light pink. And then in yellow, we'll highlight the ones that we can. And so what do we end up with? The cube root of 8 is 2. Cube root of x to the 3rd is x. Cube root of y to the 3rd is y. And then in our light pink, we have the cube root of 5x y squared. And we're done. Because it's an odd index, one solution. Okay. So we're on to our fourth objective, which I believe is our last objective for today, using the quotient property to simplify radical expressions. And once again, when we're dealing with quotients, we're dealing with division. So anything in the denominator cannot be equal to 0, because if it is, then we're dealing with undefined values, which are not possible. But something to just keep in mind, the square root of any fraction, you can separate into the square root of the numerator of that term divided by the square root of the denominator of that term. And then this slide is just the step-by-step procedure in simplifying a square root using a quotient property. All right, well, let's get into it. So we have a part A and a part B, and I feel like we skipped over. Yeah, I guess there wasn't an example 11 here. We just jumped to example 12. And so our first example, we're dealing with the square root of this fraction. What I'm going to do is I'm going to separate the numerator and denominator from each other for a moment. That numerator, which maybe we'll highlight in blue, can be broken up into two different parts, right? The largest perfect square that goes into 45 is 9, and 9 times 5 gives us our 45. And then x to the 5th is the same as x to the 4th times x. So the square root of x to the 5th is the same as the square root of x to the 4th times x. That's our new numerator. Our new denominator, square root of y to the 4th, is the same as, well, actually, that goes in perfectly, so we can keep that as is. We'll just highlight it to be, let's have it be like pink. Okay. So now let's simplify. Square root of 9 is just 3. Square root of 5 cannot be simplified. Square root of x to the 4th is x squared. And then square root of x can't be simplified. So our numerator is just 3x squared times the square root of 5x. Our denominator, square root of y to the 4th, is just y squared. And because it's an even index, right, square root has an index of 2, our final solution is plus or minus. And we're done. Let's go ahead and look at part B. cube root, so odd index, one solution. We're going to once again separate the numerator and denominator from each other to simplify first. Cube root of 27 is just 3. And then we have the cube root of x to the 7th. We can change that to the cube root of x to the 6th times the cube root of x. And then we have the cube root of y to the 3rd. That's just y. Cube root of x to the 6th is just x squared. So our final result in our numerator is just 3x times the cube root of x all over y. Once again, because it's an odd index, we only have one solution. And we're done. So that does conclude our 8.2. We've went through both 8.1 and 8.2 today just because they were both very short sections. Here are some textbook examples for additional reinforcement that I recommend you doing. But we've completed today's lesson. Let me know if you do have any questions. Next time, we'll be covering our section 8.3. All right, have a good rest of your day. Take care, everyone. Bye.